All right, everybody, today's class recording has started. So, yesterday at the beginning of class, we briefly reviewed, we compared and contrasted ionic bonding and covalent bonding. So, if we had to compare the two types, there's a couple different ways we could go. What makes them similar? What makes ionic bonding and covalent bonding similar? Julie, go ahead, give me one.
They involve electrons.
Which electrons specifically?
Valence.
Valence electrons. Eric, what's another one that we can? How else we can make them similar? Energy. What are they trying to? What are atoms trying to do? And that is not high energy, but lowest energy, right? Okay. So Julia, you said valence electrons. Specifically, how many valence electrons are we looking for? 8 valence electrons, right? And that's a low energy state. Okay. All right, and they're different because what? All right, so how are they different? What's the difference between ionic bonding and covalent bonding? Ionic bonding is transferring electrons, covalent bonding is sharing electrons. Okay? So, yesterday we introduced the concept of electronegativity. And we said electronegativity is basically a measure of how strongly an atom will attract electrons or gain electrons. Okay? So, looking at the chart of electronegativity, where are our most electronegative atoms found? Top right. We said that there's two things about them that make them strong attractors of electrons. What are the two things that make them very strongly attract electrons or want to gain electrons? There's two properties of those atoms in the top right. That's sort of an end product, is that they're highly reactive because they want to gain electrons. What makes them want to gain electrons? First, what type of elements are they? They're nonmetals, right? So that makes them gain electrons. But second, because they're in the top row, how big are they? They're pretty small. So small non-metal atoms are, generally speaking, our strongest attractors of electrons. Okay? And what type of bond we have is determined by the difference in electronegativity. We look not at the electronegativity of each individual atom, but of the difference between the two atoms that are bonded together. If the difference between electronegativities is very large, that's an ionic bond. We have one atom that really, really strongly wants to attract electrons. Another atom, not so much. That's when we end up with a complete transfer of electrons. If we have a small difference in electronegativity, we have what we call a nonpolar covalent bond. Over on the right-hand side of the board, the first covalent bond that we drew between fluorine and fluorine, right? Fluorine individually is the most electronegative atom that's on the periodic table. But of those two fluorine atoms, one is not more electronegative than the other one. They both very strongly want to attract electrons. As a result, they share those electrons real nice and even. Okay? So it's not necessarily how strongly each individual atom wants to attract electrons, it's how they compare to each other. And that leads us to our last category, which we call polar covalence. And I'm going to jump right to the bottom of your outline and talk about polar covalent using this picture, and then we'll fill in the rest of the stuff above it. Okay? So here is a covalent bond between hydrogen and chlorine. How do I know that this is a covalent bond? Both nonmetals, right? That's an indicator of what kind of bond it is. Okay? However, look at the chart on the front side of your outline and look at the difference in electronegativity between hydrogen and chlorine? What is the difference in electronegativity between these two atoms? 0.9. Okay? And if we go back to the chart a little bit higher on the back side of your outline, right? Something with a difference of 0.9 between the two atoms falls into the polar covalent category. Here's what polar covalent looks like. We have two clouds, two electron clouds in this molecule. One electron cloud surrounding hydrogen, one electron cloud surrounding chlorine. Which electron cloud is bigger? The chlorine electron cloud is bigger, even though the one is kind of light, but it's still bigger, right? Indicating what? If it has a bigger electron cloud, what does that tell us? More electrons, right? Not necessarily that's a bigger atom. It is, Jack, but, right, that density, it represents density, more electrons, right? These two electrons right in the middle, they are being shared between hydrogen and chlorine. But chlorine wants to attract them more than hydrogen does. So we end up with a situation where they are not sharing evenly, right? Chlorine wants electrons more than hydrogen. While they share unequally. And that pair of electrons spends more time around chlorine than it does around hydrogen. And we end up with a bigger electron cloud around chlorine than we do around hydrogen. Right? Now, what does that do? Well, it requires a little bit, this is a visual, right? When sodium gave its electron to chlorine, right? Remember back when we were ionic bonding, sodium gives up its electron to chlorine. Chlorine becomes a negative anion, right? Sodium becomes a positive cation. Here, it's not quite that separated. Those electrons are a little bit more tilted towards chlorine than they are towards hydrogen, but it's not total separation. So as you can see on the board, right, this gives chlorine not a negative charge, but a negative charge, right? And it gives hydrogen a positive charge, okay? Here's my real-world example to illustrate this, okay? Let's talk about chocolate milk. Okay? I know you guys have already been to lunch already, so this would be a more dangerous conversation in our normal class time because you wouldn't have been at lunch. You know, just been thinking about how much you want chocolate milk, but, you know, so. Anyway, chocolate milk. Chocolate milk is milk and chocolate syrup, right? You pour the chocolate syrup into the milk and you mix it up, right? Nice and even, right? At that point, your glass is full of chocolate milk. The chocolate milk at the top is no different than the chocolate milk at the bottom. Agreed? Okay. If you let your chocolate milk sit on the table for a while, what starts to happen? It gets warm. It gets warm. It's warm, right? It gets warm, but syrup kind of like starts settling towards the bottom, right? Does it completely separate from the milk? No. Is your glass full of chocolate milk still? Yes. But is the chocolate milk on the top the same as the chocolate milk on the bottom? Not really, right? If you take your straw and you bring it all the way down to the bottom, and you take a sip of that chocolate milk down at the bottom, is it going to taste the same as the chocolate milk on the top? No. It's not, right? It's still chocolate milk, but the top and the bottom aren't exactly the same. These two atoms are sharing electrons. They're just not really sharing evenly, right? That separated milk, that chocolate milk that has sort of settled, where the chocolate syrup is settled to the bottom, that's our example of a polar covalent bond. Some atoms have greater attraction for electrons than other atoms, right? That's what electronegativity tells you. When two non-metal atoms join together with a covalent bond, if one has a greater attraction than the other one, they're not going to share those electrons evenly. And that's going to make one side of the molecule a little bit different than the other side of the molecule. All right? That's what we call a polar covalent bond, where we have that sharing but that uneven sharing. Okay? If we have even sharing, we have a non-polar covalent bond. First, we end up with non-polar covalent bonds between two atoms that have similar attraction for electrons, or close electronegativity values. For letter B, when these atoms form a covalent bond, how do they share those electrons? Nice and evenly, or they share them equally, right? There is an even distribution of electrons between those two atoms, right? So in B, where it says when these atoms form a covalent bond, the electrons will be evenly distributed, shared evenly, something along those lines. And when that happens, we call that a non-polar covalent bond. In the chocolate milk example, this is what? No, in the chocolate milk example. When it's all nice and evenly mixed together, right? Before we stop, hold on, we're almost done. What is the milk and the chocolate syrup before you mix them together? What is that an example of? That would be like what? No. When they're completely separate. That's ionic bonding, because it's two completely separate things. Neither one of them is chocolate milk. One is milk, one is chocolate syrup. That's two different things. Go ahead.
You have the thing that says like, if the attraction is greater than like 1.7, it's an ionic bond.
Yeah.
How come like the fluorine and hydrogen bond isn't ionic bond?
It's pretty close, right? We'll talk about that when we get into next week, when we talk about how the type of bond influences the properties of those of those compounds. That's one that is a good example of how the type of bond can give it very different properties from other types of bonds. Okay.